Hello, my name is Jacob Hayes, and today I will be presenting about Lab 3. So the purpose of the lab was to apply energy and current conservation principles to predict circuit behavior, measure current and voltage using multimeters, and examine ohmic resistors and capacitors. So here are the results from the lab. The EMF, which is supplied by those two batteries that I will talk about later, was 3 volts. The drop in voltage across the 47 ohm resistor was negative 0.84 volts. And across the 100 ohm resistor was negative 1.7. The final current from the entire loop was found to be 0.46 volts, which differed from what we would think it would be, which would be 0. It took 9 seconds to charge the capacitor with a 10 ohm light bulb and 9 seconds to discharge it. And with 20 ohm light bulb, it took 40 seconds to charge and then 50 seconds to discharge. And current was the same before and after the resistors. So here are the fundamental principles involved with this lab. We have the node rule, which states that current flowing into a node must be equal to the current flowing out of it. We have the loop rule, which is that the sum of all the electric potential differences is 0. This rule is a result of the conservation of energy. We also have Ohm's law, which is voltage is equal to current times resistance. And we have capacitance, which is the idea that it's basically the ability of a system to store an electric charge. So here are the conditions from part 1. We had 2 1.5 volt batteries. We had one 47 ohm resistor and one 100 ohm resistor. We also had 2 ammeters. And the system was a circuit. Surroundings were everything else. As you can see on the right, it's a diagram of what it looked like on the electrical circuit diagram, as well as the actual experimental setup. So here is a procedure for part 1. I'll let you take a quick read of that now. Here are the results from part 1. The expected current was found to be 0.2 amps. However, the measured current was actually 0.018 amps, so a magnitude of 10 lower than expected. The battery was 3.0 volts. The drop in voltage across the 47 ohm resistor was negative 0.84 volts. And across the 100 ohm resistor, it was negative 1.7 volts. And at the end, across the entire loop, the voltage was found to be 0.46 volts, which differed from what we would expect. As you can see on the right, that is what we would expect. So here are the resistance calculations shown on the left for each of the circuit components that are important. So the ammeter read 0.017 when the voltmeter was connected across the 100 ohm resistor. This current value remained roughly the same because the voltmeter, which acts as a super resistor essentially, was positioned in parallel. And the current in the other ammeter increased to 0.06 amperes, so quite a bit, when the voltmeter was replaced by an ammeter in parallel. And this occurs because the ammeter has a very low resistance, which leads to current flowing through it instead of the resistor. So here are the conditions from part 2. Still the 2 batteries. We had now 2 resistors that were light bulbs. One was 10 ohm and one 20 ohm. And we also had a capacitor now. So you can see on the right, that's the setup. So here's a procedure for part 2. And here are the results from part 2. For the 10 ohm light bulb, it took 9 seconds to charge the capacitor and then 9 seconds to discharge it. And for the 20 ohm light bulb, it took 40 seconds to charge it and then 50 seconds to discharge it. So the light bulb started glowing for both of these scenarios. However, when the battery is supplying the current, for one of the scenarios, and for the other, the capacitor was supplying the current through the battery, or through the light bulb, excuse me. So here are some of the assumptions made about this lab. We assume there are zero resistors zero resistance in wires and ammeters, and that the batteries were fully charged and produced exactly 1.5 volts each. So here are some possible sources of error. We could have had human error and with stopwatch timing, as well as imprecise ammeter and voltmeter readings. So what if we charge a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? And would this prediction happen in real life? Well, if you did this, the ideal model would actually predict the capacitor to charge immediately. However, this would not happen because in real life, batteries have internal resistance. So we were tasked with using an ammeter to measure how long it takes to charge the capacitor when it was connected directly to the battery, and the ammeter, of course. So we found that time to be 14.8 seconds. And when using the ammeter, the capacitor charges more slowly than predicted because of the resistance from the battery, wires, and everything else in the circuit. So the predicted charging time is shorter because the ideal model does not take into account the actual resistance from the battery wires or the capacitor. Thank you for your time.